Hello everyone. In this video, I will show you a very important result in Calculus 1. This result is called the fundamental theorem of calculus. So in this video, I will show you the second fundamental theorem of calculus. So if we write the accumulation function fx uh, as the integral from a number a to x and f of t dt. So let's suppose this is the graph of the function y equals f of t. Now in this coordinate system, the horizontal axis is the t-axis and the vertical axis is the y-axis. According to what we saw in the previous video about the definition of accumulation function, now we can see this function fx is equal to the area of this region, the region bounded by this curve y equals ft and bounded by the horizontal axis and bounded by the number a and this variable x, which is this blue region. Okay, now if we increase the x a little bit, just a little bit, a very small amount, so I increase x to x plus h, then we can define another accumulation function f of x plus h. So the function value of f of x plus h is the region bounded between this number a and this variable x plus h, and between this curve and the horizontal axis, right? So therefore, the difference between these two functions will be this region, will be the area of this green region, right? And since we assume that we just increase x a little bit, so the difference between x and x plus h, we know that is h. Since we assume that we increase x a little bit, so the difference between these two is h. Okay, so since we assume x is increased a little bit, so this green region can be approximated by a rectangle. Okay, so the area of this green region we can write as fx, little fx times h, where h stands for the width of this rectangle, and f of x stands for the height of this rectangle. So the difference of these two accumulation functions is around to the product of h and little fx, right? Okay, now if we divide by h on both sides, so the difference of capital X plus h minus capital fx over h is approximated by little fx. Okay, again, little f stands for the function of this curve, and the capital F is the culmination function. Okay. Now, if we take the limit on both sides as h approaches 0, according to the definition of derivative, the limit of this quotient, as h approaches 0, we can write this as f prime of x, right? And on the right hand side, because when we take the limit of little fx as h approaches 0, the result will be equal to itself. Why? Because the little fx has nothing to do with h. So this is like you take a limit of a constant, and the result will be equal to that constant. So when we take the limit of this, the result will be equal to little fx. And since the limit of this quotient is equal to the derivative of capital Fx, therefore we have this result. That is the derivative of the culmination function capital Fx equals the little fx. Okay. In other words, when we are taking the derivative of this integral, we are from a to x of ft dt, the result will be equal to this function little f, and the input is the x. Okay, so this is what the second fundamental theorem of calculus tells us. If f is continuous on an open interval I and containing the point A, then for every x in the interval, when we take the derivative of this integral, the result equals the little fx. Okay, so the second fundamental theorem of calculus shows us how an accumulation function is related to the function little f. Okay, so their relationship is the derivative of this accumulation function will be equal to this function f with the with the x plugin. Okay. All right. So let's use this result to try these examples. Okay, we want to find the derivative of the function fx, where fx is defined by integral. Okay, so here now this fx is our accumulation function, right? So we want to know what is the derivative of this. Now this function, the square root of t squared plus 1, is like the ft in the formula. Okay, so according to this result, the derivative of this accumulation function will be equal to this function with the x plugin. So that will be the square root of, we just change t into x squared plus 1. So the derivative of the little fx equals the square root of x squared plus 1. Okay, let's see another one. The derivative of the little fx will be equal to this function cosine with the x plugin. So equals cosine of x squared plus 2x plus 1. Now for this one, we cannot use the result directly. because in this result, you see the lower bound is a constant, is a number, and the upper bound is the variable, is the x. However, here the lower bound is the variable and the upper bound is the number. So before we can use this result, we need to rewrite this integral a little bit. We need to switch the lower bound with the upper bound. And in the previous lecture, we said when we switch the lower bound with the upper bound, we will change the integral into the opposite. So we add a negative sign. Okay. Okay. So now once fx is returned into this integral, then to find the derivative, we can use the result from the second fundamental theorem of calculus. So the derivative of this function is negative this function t squared over t plus 1. We plug we plug x into the function. So that is x squared over x plus 1.